But most of the presentation today will be taken by Paul Bailey. Paul Bailey is a geotechnical engineer who's working in Arab. He has a wealth of experience. He's been working on a number of projects such as the Commonwealth Institute in London, the Fehmarn Belt Tunnel, which connects Denmark to Germany. So there are a number of projects that he has worked on. But Paul has also recently completed an MSc in soil mechanics at Imperial College, London. And as part of his dissertation, he focused on TZ curves and also thermal pile loading. So that is what Paul will be presenting today, and that was what was used to develop Oasys Pile to make Oasys Pile 19.5. So without much further ado, I'm actually going to transfer now to Paul.
Hi, so thanks for joining this webinar on Oasys Pile. I'll just move straight on to the webinar objectives, and I've got 3 objectives for this webinar today. Firstly, to introduce the recent improvements that have been implemented in the update to Oasys Pile, which is now available on the Oasys website. Secondly, I'll present a few scenarios that can be analysed with Oasys Pile. Some of these scenarios could have previously been analysed with the older versions of the program, but some of them use the new program features as well. And finally, I'll just wrap up with a brief case study of a scenario that we back analysed. A field test, a thermal pile field test, and just take you through the Oasys Pile program and show you how to use some of the new features. So if we look at the first objective, the program updates that have been included in this version of the new version of the program mostly concentrate around the settlement part of the program. So if you're familiar with using Oasys Pile already, you'll be aware that there's a capacity part of the program and a settlement part. So these 3 updates, settlement analysis using TZ curves, staged loading and thermal loading, all apply to the settlement part of the program. So settlement analysis using TZ curves has been added based on the theory of load transfer curves, and staged loading has been updated to allow a number of loading stages to be applied to pile analysis, so you can load and unload and reload the pile, and look at how the settlement or the settlement of the pile changes at different loading stages. And finally, thermal loading has been added to allow analysis of thermal piles to be carried out. So the picture on the right shows a thermal pile being installed in London, and those are becoming increasingly common. So I'll go into some of the more detailed description of these 3 updates. So the first update on TZ curves. If I just provide you with a little bit of the theory of TZ curves, I'll try not to bore you with too much detail, but if you look at the figure on the right-hand side, in order to set up a TZ model, the pile is split up into a number of different elements, and springs are attached to each element. So the springs down the center of the pile model the pile axial stiffness based on the Young's modulus of the concrete of the pile, while the springs to the right-hand side then would model the soil behavior. And you can have different shapes of different types of springs, perhaps a non-linear spring to model non-linear soil behavior, and those springs are the TZ load displacement springs on the right-hand side of the pile elements. The TZ springs then are based on soil stress strain behavior, and so providing the soil stress strain behavior is understood, then you can model the TZ springs quite well. If I just then describe how you go from the soil stress strain behavior to to a low displacement or TZ spring. For the pile, there's two different scenarios really: the pile shaft and the pile base. And the pile shaft assumes that there are concentric cylinders of shearing soil extending outwards from the pile, and an integration then of all these shear stresses is carried out to determine the total load that can be carried by the pile, and the load displacement relationship can then be calculated, and that's based on a limiting radius from the pile of where your shear stress reduces to zero. Meanwhile, the pile base, the relationship for the pile base is based on elasticity theory of a rigid punch, and that's described further in Timoshenko and Goodyear's book, which is included in the references in the pile help file. So the TZ curves that we've included in the program, there are 6 that can be input, and these are listed on this page. So the elastic plastic TZ curves are with the various references that are used. So these TZ curves are all described in the help file with some detail, and if you need to refer to the references for further information, then that's possible. Also, the references are given in the help file. But it might just be easier to see a figure of what each of these TZ curves actually looks like. So if I just step through them one at a time, the elastic plastic TZ curves are basically it's basically a linear elastic relationship up to a yield point where then perfectly plastic displacement occurs with no increase in load, and the kind of the yield point would occur at your limiting shaft resistance or limiting base resistance that you input through the soil parameters for your pile. And so then the next type of curve is a hyperbolic relationship, and so this allows maybe a more accurate representation of the soil properties with the reducing stiffness as displacement increases up until a similar yield point where plastic displacement then occurs. The third set of TZ curves that we've implemented are called logarithmic curves, and these are very similar to the type of curves that are used in Mark Randolph's RATS program. The first part of the curve is a linear elastic portion similar to the elastic plastic curves. However, after the initial linear elastic portion of the curve, there's a logarithmic function up to the peak shaft resistance or peak base resistance, the peak load value of the curve, and then the final portion of the curve is an exponential decay down to some degraded shaft or base resistance. So where you have soil properties that might show some degradation with increasing strain or increasing cycles, you might want to include a feature like that. So the only difference really between this curve and Mark Randolph's RATS program is that RATS uses a parabolic curve for the central portion of the TZ curve, whereas we're using a logarithmic function, and full description of the difference between the two is provided in my MSc thesis, which I think is available on the Oasys website. But the advantage of the logarithmic function is that the displacement to peak load can be set as an actual distance or length, so or displacement. So it means that some people might choose 0.5 or 1% of the pile diameter as a displacement where peak peak load is reached on the pile shaft, and if then this using logarithmic TZ curves would allow you to choose the best displacement that actually matches the field test data. Then the API curves, so the American Petroleum Institute have proposed some TZ curves in their guidance, and these are these are implemented into the program as well. So there's curves for clay and sand that just follow the relationship that's set out in the API. The fifth set of curves is based on a reference from Via Vergia, who proposed a parabolic function up to peak stress, followed by a perfectly plastic displacement post peak, and finally, if the previous curves aren't what you're looking for, then these are defined functions quite useful to input just the exact relationship that you want to follow. So those are the TZ curves that we've implemented into the program, and then the second upgrade that we've added is to allow staged loading to be carried out. So if you're familiar with the other Oasys programs, you might recognize the kind of stage tree view box, which allows you to add new stages and to change some of the parameters at different stages, such as your load or thermal load and solid profile and water data can all be changed at each loading stage. The staged loading can only be used then with TZ curves, so they go hand in hand, because assumptions need to be used to calculate what actually happens to the TZ curve upon unloading and reloading. So the assumptions are all set out quite clearly in the help file, but just to give you a brief description of the kind of assumptions that we need to consider is shown on the diagram on the right hand side. So you might have an initial TZ curve where you're initially loading up to some kind of peak load or peak stress. Then when you unload, there's a criteria called Masing's criteria, which assumes that the unloading curve is similar to the initial loading curve, only doubled in height and doubled in size. So you unload to some kind of negative strain and negative stress, and then when you reload again, you can apply different assumptions on the degradation of shear modulus or degradation of the peak stress that's reached upon reloading again. So those are some of the assumptions that need to be considered when you're unloading and reloading, and those assumptions are set out in the help file, as I said, and for each different type of TZ curve, there's the assumptions are set out of what has been considered. Then the third update to the program includes the ability to analyze thermal loads on the pile. So, for example, where thermal piles are installed in the ground, it seems to be becoming increasingly popular recently, and these piles are similar to board piles, only they include pipes that are attached to the reinforcement cage, plastic pipes that can be water can then be circulated through the pile at a later date once the pile has been completed and concreted. So these reinforcement cages on the right hand side show what the cage looks like before it's been installed in the ground, and once the thermal pile has been installed, then water can be circulated in the pile to assist the heating and cooling requirements of the building above. So just using the kind of steady ground temperature, it's possible to circulate water through the pile. Either hot water can be put into the pile, which then comes out slightly colder, or cold water can be put into the pile and it comes out slightly warmer, and that temperature difference can be used to heat the building above ground. However, the the complicated part is that with the pile heating and cooling, then if you're pumping hot water or cold water into your pile and the pile starts to heat up, there's an associated expansion and contraction of the pile in the ground, and that affects the settlement and the mobilized shaft friction and the axial stress that occurs in your pile. So the updates to the program allow this effect to be considered, but I just should point out that it's purely the effect of the change in strain in the pile and the change in length, the axial expansion and contraction, and no temperature effects on the soil properties around the pile are considered at all. That seems to be another topic that's receiving a lot of research interest at the minute, and it hasn't been overly conclusive just yet, the actual temperature effects on soil properties, so those haven't been included in the program, but the axial expansion and contraction and the effect of that on the shear, the mobilized shaft friction has been included in the program. So to move on to the second objective of the webinar, I'll just briefly talk through some of the scenarios in which Oasys Pile can be quite useful. The first scenario to consider heave-induced pile tension. It could possibly already be could be analysed using previous versions of the program. However, the new updates to the program using TZ curves and the ability to split the pile up into a number of elements and apply different TZ curves down the length of the pile just increases the accuracy of carrying out an analysis such as this. So, for example, if you have a pile in heaving ground at the base of a basement excavation, you might have positive shear strain and above the neutral point and negative shear strain below the neutral point, which result in shear stress, mobilized shear stress along the pile shaft in different directions, and you'll be able to calculate the maximum tensile force in the pile from that analysis. The opposite would also be true if you considered negative skin friction on your piles. So you might have piles installed in soft ground or with a settling layer at the top of the pile, and want to consider any increase in compressive stress in your pile as a result of this effect. And again, the TZ curves just make the analysis of negative skin friction slightly more accurate with the ability to model a range of soil layers and a range of TZ curves down the length of your pile. So you might have quite a soft, low stiffness layer at the top of your pile, and you could adjust the properties of the TZ springs accordingly to match that layer, and then you might have a more competent layer at depth. The third scenario would be to consider cyclic mechanical loading, and this could be so this uses the staged loading feature that has been added, and it could be quite from one extreme, perhaps offshore foundations where thousands or tens of thousands or millions of cycles might be applied to loading cycles might be experienced by the foundation, or it could be something maybe smaller scale, like a simple pile load test where you have a number of loading stages or perhaps loading and unloading stages carried out during a pile load test. And then the final scenario that you could analyze would be a cyclic thermal loading analysis, and so that could be the thermal pile over its full lifetime of, say, 100 years, and you might have annual cycles of heating and cooling applied to the pile, or it could be something smaller scale where you might have a thermal pile test with just a few cycles. So this final feature uses both the really uses all three of the program updates. So it would use the TZ curves, the stage loading, and the thermal loading updates. So just to move on to the final objective then, to talk through one of the case studies. This is a cyclic thermal loading case study that I want to look at. So the case study is taken from an ongoing construction project in London where we were asked to look at the feasibility of thermal piles as part of the foundation scheme. And so we installed a 300 millimeter diameter mini pile into the London clay, and as part of the installation we installed a plastic U-tube pipe and also 4 levels of vibrating wire strain gauges were installed as well to look at the effects of heating and cooling the thermal mini pile. So then, as part of the test, over the course of about a month, we heated and cooled the pile by pumping hot water and alternatively cold water around the plastic pipe that was cast inside the pile. So once the pile had kind of reached an equilibrium temperature of it came to about 18 degrees after the concrete had cured, and we started to heat the pile in the first stage up to 29 degrees. Before we let it recover, and then we cooled the pile in stage 2 down to about 8 degrees before we let it recover. Cooled it a second time, so in the third stage it was cooled again to about 8 degrees, let it recover before in the final stage of the test we heated the pile to about 26 degrees. So hopefully I can transfer from here to the Oasys Pile program and just show you how this test was back analyzed. So this is the updated Oasys Pile program, and most of these titles down the left hand side should be familiar with people using Oasys programs, and if you've used the Oasys Pile program before, most of these titles remain the same. However, the additional items that have been added as part of the updates include this area of the program here, where under material properties we can now input TZ curve data, and we've got the 6 types of TZ curves. So these are TZ curves that are applied to the pile shaft. And then we've got tip load curve data, and we've got the same 6 sets of curves that are for the pile base. Then the other features that have been added, the thermal and cyclic loading box, where you can input your thermal loading or a number of loading cycles, mechanical or thermal, and then the stage tree view, as I described earlier, is where the different loading stages are applied. So if I just close that and kind of go back through, so those are where the updates have been put into the program. But if I just go back and talk through the analysis of this thermal mini pile case study, and firstly, if we look at the analysis options box and make sure that settlement is selected. So these are the 2 areas of the program that can be used, capacity or settlement. And we've been focusing on settlement today. Then if we look at the settlement data input, we now have a choice between Mindlin or TZ curves. So previously the program only used the Mindlin method of calculation, and if you've used the program before, you should recognize the input of the Young's modulus of the soil above the toe and below the toe is input in this area of the program. However, when we're using TZ curves, we don't put the soil properties in here. We put the soil properties in the TZ area, in the kind of stiffness and everything goes into the TZ area of the program, and we can split it up as before into a number of elements. So this pile is just in 10 elements. So then if we look at the material properties, I've used undrained materials, and this is kind of similar to what we had in the previous version of the program. However, additional items are that now we have to select a TZ curve to accompany. So both on the shaft, we need to select a TZ curve to accompany the material on the pile shaft. And if we also scroll across to the base, we need to select a tip load curve or a TZ curve for the base as well. So you might notice that for the base of this pile, I've put in NC of 0, so that means that we're ignoring any contribution to the capacity of the pile that would come from the pile base, just because it took a while for the installation to be carried out, and we were concerned that the base might have softened, and we decided to ignore the base capacity. But if we look at the shaft TZ curves, so these labels refer to the TZ curves then that are input in this part of the program. So we've got shaft log 1 and log 2. These are the logarithmic curves that I've used with a Young's modulus at the top, and we can apply a gradient so that at every element the program calculates what the stiffness of the spring, kind of the elastic stiffness, should be, based on the Young's modulus and the Poisson's ratio. And then we've got the shaft radius, boundary radius of where those shear stresses would reduce to 0. And I should just note that that's quite a large number. People are maybe a little bit surprised that the area of shear around the pile is such a high number. However, just note that would be the elastic whenever the shear stresses are still in the elastic range. So whenever the pile starts to fail, you would think of the kind of radius of shearing being quite in a small range. However, this isn't the same. This large numbers is when you're considering elastic cylinders of shearing soil. Then this psi value is the parameter for, if you remember, the logarithmic curves are split into 3 portions. So the first portion is a linear portion, and this psi value just dictates the length, the kind of extent of that linear portion. So this is a value between 0 and 1, where 0 means that we have no linear portion, and immediately we start into a logarithmic function. Then W peak is the displacement that's required to reach peak stress, and we've chosen to use 0.5% of the pile diameter, so 300 millimeter pile, and then the size soft value. Then these final 3 parameters relate to the exponential decay part of the logarithmic TZ curve, and if you want to have a degrading portion of the curve, then this value is between 0 and 1 again, where 1 means that there's no degradation post peak, and if you want to degrade to a certain stress or load value, put in a value less than 1, and you can have a displacement that these final 2 values just set the rate at which the exponential degradation would occur post peak. So if I then move on, close those 2 and move on to the stage tree view, then where the different cyclic loading stages have been input. So the stage 0 is where we've installed the pile and we start to heat it up, and the input that's required is in the thermal and cyclic loading part. So we've we need to input the temperature change over the ambient temperature. So if you remember the the temperatures that were carried out for our case study pile test, we heated the pile from about 18 degrees up to 29 degrees. So that's where the increase of 11 degrees comes from. Then in the next stage, we recovered back to ambient temperature. So a zero change in from the ambient temperature, we've assumed is zero change. Then we cool the pile again. We carried the first cooling stage, where we cooled the pile from from the ambient temperature of 18 down to about 8 degrees. So that's our change in temperature of minus 10 degrees. Then we carried out a recovery stage where we went back to ambient temperature. A second cooling stage where we cooled from 18 down to about 9 degrees. Recovered back to ambient temperature before the final stage. We heated again from about 18 up to 26 degrees, which is where all those numbers come from. So hopefully when I press analyze, we can look at some results. So if I we can look at results from either capacity or settlement, and I'll just for now we'll look at the stresses and displacement along the pile, and usually the graphical output is a bit more easier to handle. So in the graphical output, we're given a view of the pile with the limiting shaft friction. We've input a solid profile that increases in strength with depth and the corresponding increase in limiting shaft friction. Then we can look at the actual mobilized shaft friction, the pile stress, and the pile displacement. Also, I forgot to point out that we've accompanying the stage 3 view, we have these arrows that we can cycle through the different stages of the pile test. So I'll just move back to stage 0, and we'll go through the results in order. So the first stage of heating the pile results in thermal expansion of the pile, which as we can see from this red line, the pile displacement, we've got negative displacement towards the top of the pile, which is the pile moving upwards, and positive displacement towards the toe of the pile, which is the pile moving downwards, and the neutral point somewhere just below the middle of the pile. Associated with this upwards and downwards movement, we've got two directions of mobilized shaft resistance, so negative above the neutral point and positive below. Then, in order to understand the pile axial stress, if we think about the pile trying to expand but being resisted by the soil around it, we've got because of that effect. And even though we've got no external load applied to the pile, just the kind of internal expansion of the pile induces this compressive stress in the pile, and we can work out the maximum compressive stress at the midpoint of the pile and take that into account in design. Then when we return to ambient temperature, there's a slight residual stress and displacement, and then when we go to the first cooling stage, the opposite effects occur so this pile is cooling and trying to contract, so the top of the pile is moving downwards and the base of the pile is moving upwards with different directions of immobilized shaft friction, and as a result of the cooling and contracting pile, then we have a tensile stress that's induced in the pile this time, and we can calculate the maximum tensile stress at the midpoint of the pile again, or sorry, at the neutral point of the pile. And then if we cycle through the rest of the cycles, we have the same effect. So again, the second cooling cycle followed by the final heating. If I just show you as well the effect of in the pile properties box, we can change some parameters. So there's a new feature. The thermal loading takes into account the thermal coefficient of expansion, the linear coefficient of thermal expansion of the pile, which is input into the program in this box, and also whether the pile head is free or fixed. So in this analysis that I just showed you, we assumed that the pile head was free to move up or down, without any limitation from surrounding piles or pile caps or overhead structure. And if we wanted to change that to a fixed head, then that would affect our results. And I'll just show you the effect of that briefly. So this is the 300 millimeter diameter pile, and if we just look at the same results that we looked at previously, now on the final heating stage, instead of the axial stress reducing to 0 at the top, it comes to a maximum where the limit, the kind of restricting effect of the structure is inducing quite a large axial stress. So at the top of the pile, we've got 0 displacement and therefore 0 mobilized shaft friction, and increasing displacement at depth. However, our maximum axial stress is now at the top of the pile. So those are different considerations that you can use whenever you're back analyzing thermal piles, and the program lets you carry out these considerations quite well. If I just go back then to the PowerPoint slides and wrap up. So just to talk through a summary of the results of the case study, we looked at about 26 meter pile with 4 levels of strain gauges, and on the figure on the graph on the right hand side, then I've provided a comparison between the data from the strain gauges and the kind of back analyzed results from Oasys Pile. And so, for example, on the positive axial force, we're looking at the results from heating, where the dotted lines with points are the strain gauge results, data points, and this kind of smoother dashed lines are the results from Oasys Pile. And we can see that whenever we've assumed a fixed pile head for the heating stages, that we get quite a good match to the results from the case study. However, when we look at the cooling stages on the left hand side of this graph, again, so the solid smooth lines are the Oasys Pile results, and the dashed lines with the data points are the the pile head perhaps cracks during cooling or during the contraction of the pile. Maybe some cracking might allow you to assume a free pile head. We still don't get a very good match to the results, and that could be down to some of the considerations of the thermal effect on solid properties that I mentioned earlier that isn't considered by the program, and is the subject of further research. So just to recap on the objectives of the webinar today, the first was to introduce the recent improvements that have been added to Oasys Pile, and in summary those are TZ curves, staged loading and thermal loading. Then I presented a few scenarios that you could use to analyze using the new program features, and we mentioned heave-induced pile tension negative skin friction, cyclic, mechanical loading, and again that could either be some large scale or long-term offshore foundation, or something smaller, more short-term pile load test, and finally cyclic thermal loading. And with the cyclic thermal loading, then we talked through a little case study that uses all three of the new program features, and talked through some of the results, and just explained how where the new program features are found, and how you could go about using them. So hopefully I haven't gone through that too quickly, and you can if we just explain that the help file is quite useful to find further details of which TZ curves you can use, and how they behave, and the assumptions behind all of the updates. So it's possible to get a free 30-day trial, and the help files should be available with that, or online as well, and you can study for yourself just exactly how you would be how you'd like to use the new program features. Also online there's some tutorial videos which explain, I think there's 3 different videos on the new features. And finally, feel free to contact Oasys or look on the website for further information.